Your GPU is cooked, not broken, not outdated, genuinely, physically, thermodynamically cooked. And the people building the next generation of AI know it. A company in Germany just plugged a chip into a supercomputer that doesn't use electricity to think. It uses light. Literal, actual, physics-bending light. And it's not a concept. It's not a PowerPoint. It's running right now inside one of Europe's biggest supercomputers. First, why your GPU is in trouble. Your graphics card, the thing gamers worship and AI researchers mortgage their houses for, has over 10,000 cores. Each one is basically a tiny calculator that can do one thing really fast. Math. Simple math. Addition, multiplication, that kind of stuff. To run something like Cyberpunk 2077, your GPU needs to do about 36 trillion calculations every single second, which sounds insane. And it is. If every person on Earth did one calculation per second, we'd still need 4,400 entire planets full of people to match what your GPU does. That's wild. But here's the problem. All of that math, it generates heat. A lot of heat. If your GPU pulls 500 watts of power, all 500 watts eventually becomes heat. Because information, the thing your GPU is actually producing, has no physical mass, no weight, no energy. So all that power has literally nowhere to go, except out as heat. Your GPU is basically a space heater that also plays video games. Now scale that up to an AI data center running something like ChatGPT, and things get embarrassing. ChatGPT alone burns through over 564 megawatt hours of electricity every single day. To put that in perspective, that's about 100 times what an average German household uses in an entire year. I'll let that sink in. And cooling alone, just keeping the hardware from melting itself, eats up to 40% of a data center's total energy. Not computing, not networking, just cooling. That's like nearly half your electric bill going towards keeping your fridge cold while the fridge does nothing. So why can't we just make better GPUs? Well, here's the thing. For decades, we had this rule called Moore's Law. Every 2 years, the number of transistors you could fit on a chip would double. More transistors equals more power. It was basically free performance upgrades on a timer. Your phone today is more powerful than a room-sized computer from the 1970s, entirely because of this rule. But then, we hit a wall. Transistors are now so small, they're approaching the size of individual atoms. And at that scale, physics starts working against you. Electrons start jumping across gaps they're not supposed to cross. That's called quantum tunneling. And suddenly your chip is doing random stuff nobody asked for. You literally cannot shrink transistors any further without the laws of physics laughing in your face. So the industry basically decided, we can't go smaller, so we go bigger. More chips, more servers, more data centers, more power, which dumps us right back into the heat problem. It's a nightmare loop. Enter photons, which sounds like a Marvel character, but bear with me. Photonic chips don't compute with electrons at all. They use photons, particles of light, and that one swap changes basically everything. Light doesn't have mass, so it doesn't grind against material, create resistance, or produce heat the way electrons do. On a normal GPU, electrical resistance is the single biggest reason for all that heat. Photonic chips sidestep that entirely. Zero heat generated on the chip itself, not less heat. Zero. Light also moves faster than electrons crawling through a wire, way faster. Electronics operate in the gigahertz range. Light operates in the hundreds of terahertz range. That's not a small difference. That's like comparing a bicycle to a fighter jet. But here's the part that actually made my brain short circuit. A single beam of light can carry multiple, completely independent streams of data at the same time by using different wavelengths. Basically different colors of light. Your phone does one data stream. Light does dozens simultaneously through the exact same pathway. Electrons physically cannot do that. It's like comparing a 1-lane dirt road to a 64-lane superhighway, where all the lanes exist in the same physical space at the same time. This technique is called wavelength division multiplexing. And yes, that name sounds like someone fell asleep on a keyboard, but the concept is simple. Different colors, different data, same beam, all at once. The math part is where things get genuinely weird. On a traditional GPU, if you want to multiply two giant matrices together, which is basically all AI does, just that, over and over and over, you need millions of transistors flipping on and off across multiple clock cycles, brute forcing the answer step by step. On a photonic chip, you shine the light through a specially shaped optical element. As the different wavelengths of light pass through and intersect, they create interference patterns. And that interference pattern, the way the waves reinforce or cancel each other, is the mathematical answer. The math literally solves itself as the light travels through the material. No clock cycles, no fetch and execute. The physics does the homework. It's kind of like if you could add two numbers together just by letting them exist near each other. Except it's real and it works, and it's inside a supercomputer in Germany right now. The chip behind this comes from Q.ant, based in Stuttgart, and what they've done is wild. In July 2025, they deployed their first photonic processor at the Leibniz Supercomputing Center LRZ in Garching, a real supercomputing facility handling real workloads. Then in March 2026, they launched their Gen 2 chip at the same site, and the jump is massive. 50 times higher throughput for matrix multiplications, 25 times faster image recognition, up to 90 times lower power use, and up to 100 times more effective data center capacity. Plus, it generates zero on-chip heat, cutting the need for massive cooling systems. Q.ant's CEO says they achieved in 1 year what digital computing took a decade to do, and the Gen 1 to Gen 2 leap proves it. And it's not just them. Researchers at Tsinghua University and Shanghai Jiao Tong University built an optical processor with over 2 million photonic neurons, outperforming Nvidia GPUs by 100 times on specific tasks. This isn't isolated, it's a global race, and it's accelerating fast. But there is a catch though. Photonic chips are extremely good at math, but they can't store data. There's no optical memory yet. So when they need data, they have to get it from normal electronic memory. Each time data switches between light and electricity, it wastes time and energy. This is called the conversion penalty. They also can't do everything. They are great at tasks like calculations and AI, but not general work. So regular CPUs or GPUs are still needed. That's why current systems use both. Photonic chips for heavy math, silicon chips for everything else. Making these chips is also difficult. Q.ant uses a special material called thin film lithium niobate, which is not yet easy to produce at large scale, so manufacturing is still improving. So, where does this go from here? Photonic computing isn't replacing your PC anytime soon. The real issue is AI growing faster than power grids can handle. You can't keep scaling data centers forever. Something has to change. A 90 times drop in power use isn't small. It changes how AI can scale. By 2030, photonic coprocessors will likely be used in high-performance fields like research, climate modeling, medical imaging, and large AI systems. After that, if memory and manufacturing improve, adoption could expand further. What Q.ant proved at the Leibniz Supercomputing Center shows this works outside labs. GPUs won't disappear, but they may not be the only answer.